I want to now talk about singularities and how we can find singularities and how we can possibly avoid some of these singularities as we deal with kinematics of robotic manipulators. So singularities are tied to the Jacobian, and whenever the Jacobian is not invertible, that means we are at singularity. So singularity and Jacobian go side by side, and we always like the Jacobian to be invertible so that we do not have singularity in our robot. We're going to talk about two different singularities. The first one is momentary singularity. So as the name suggests, it's a momentary, which means that it can be, you can get out of that singularity. And usually this happens when the configuration of the arm is causing that singularity. So if you move the arm such that that configuration is changed, you can get out of that singularity or you can avoid it by not going to that configuration to start with. The other kind is a permanent singularity, which is basically permanently makes your arm permanently singular because you're trying to control Cartesian degrees of freedom without having the ability to control them from your joint space. For example, if I have 3 joints in my robotic arm, I can only control 3 Cartesian velocities. For example, maybe I can control x dot and y dot and z dot, or maybe x dot, y dot, and omega y, and so forth. And we're going to look at an example of how to choose our Jacobian so that we do not get a permanent singularity for our robot. Now, let's say we have a square Jacobian, which means that the number of degrees of freedom or number of joints that I have equals to the number of Cartesian coordinate velocities that I'm trying to control. Okay, so let's say I have 4 joints and I'm controlling only 4 Cartesian coordinates and have a square Jacobian. In that case, we can look at the forward kinematics such that we use the Jacobian and we multiply it by the joint velocities and we get the Cartesian velocities. Now, if we look at the inverse of the Jacobian, that would make inverse kinematics here. So we are given the Cartesian velocities. We use the inverse of the Jacobian to find the joint velocities. So forward kinematics, we use Jacobian. Inverse kinematics, we use inverse of the Jacobian. Okay, so to find the inverse of the Jacobian, when we do inverse kinematics, we always have to include or check the determinant of the Jacobian. Because to find the inverse, of course, you have to divide the conjugate of the Jacobian by the determinant of the Jacobian. So the determinant of the Jacobian can be a good indicator of singularity. If the determinant of the Jacobian does not equal to 0, that means J is invertible. Okay, so that's a good case right here. Now, when the determinant of Jacobian is almost 0, but it's not quite 0, that means J is invertible, but we're going to have very dangerous joint velocities that might cause us to go out of control, or the robot will go out of control. So again, we do not want to have determinant to be close to 0. Now, if determinant is equal to 0, that means J is not invertible. So in that case, of course, we cannot perform the inverse kinematics and find any motions in that case. Now let's talk about these singularity types one type at a time. Let's start with the first type, momentary singularities. And these happen when the configuration of the robot at that particular moment, or any particular moment, has a momentary loss of 1 or more degrees of freedom. So if you have 4 joints, 5 joints, you are momentarily losing one of these joints or the action of one of these joints due to the configuration of the robot. And there are 2 cases for this particular type of singularity. The first case is workspace boundary singularity. And what it is basically is when the arm is fully stretched or the arm is fully folded on itself. So when it's fully stretched, that means it's reaching the edge, the outer edge of the workspace. When it's fully folded on itself, it's reaching the inner edge of its workspace. So in that case, we are reaching a workspace boundary singularity. The second case is workspace interior singularity. So you may not be close to the edge of your workspace, but in this case, you have 1 or more joints lined up together. And what I mean by lined up is that if they are lined up such that if you move any of these 2 joints that are lined up, the end effector will produce exactly the same motion. Whether it's prismatic joints, two prismatic joints that are lined up together and making the same action, whether you move one or the other, or if it's a revolute joint, that's both of the joints are aligned together, and if any motion of either one of these two produces the exact same motion at the end effector, that means they are both combined into one joint and you lost one of the degrees of freedom momentarily. Now let's take an example on this. We have the classic 2R robot here with two joints and two links and the end effector. And for this planar robot, we want to find when does the robot become singular, and then find the inverse of the Jacobian for that robot and the joint velocities in terms of Cartesian velocities. As we saw earlier, we can find the Jacobian relative to frame 3, and we have it right here. And we are going to use that Jacobian to find out when does it become singular and try to invert this Jacobian. To start the solution for this problem, let's look at the determinant of the Jacobian. As we saw earlier, the determinant of the Jacobian here has to be set to 0 in order for me to have a singularity. So since the Jacobian is given, I just have to find the determinant of the Jacobian, which is the diagonal elements minus the off-diagonal elements, and that would give me L1, L2 times S2. Now if I want to set this quantity here to 0, that means I need to find out what makes this quantity to equal 0. As we know, L1 and L2 are lengths, so they cannot be zeros. That means S2 has to be 0 in order for this quantity to be 0. Now for S2, which is sine of theta 2, to be 0, it has to be, theta 2 has to be either 0 or 180, because sine 0 is 0 and sine 180 is 0. So that's the two quantities that would be making it possible for this determinant to be 0. Now as you can see here, there's no mentioning of theta 1 at all, which means theta 1 does not play any role in having this robot becoming singular. And we're going to see this in the drawing that we're going to see right now. So these are the two cases. The first case is when theta 2 equals to 0. And in that case, the arm is fully stretched, and this angle here is 0. And at the end effector here, we are right at the outer boundary of our workspace. So if you notice here, it doesn't matter what theta 1 is. Theta 1 can be any value. If theta 2 is 0, that means we are always at the outer boundary of our robot. Okay. Now when we look at the second case, when theta 2 equals to 180, that means we are at the inner boundary and the arm is fully folded on itself. And that particular point, which is the end effector point, is right at the border of the inner boundary of my robot right here. And that inner boundary is causing singularity as well. So again, it doesn't matter what theta 1 is, as long as theta 2 is 180, theta 1 does not matter for this particular case. All right, now we can go ahead and start looking at the inverse of the Jacobian. And there are several ways to find the inverse of the Jacobian. This way here we use the determinant of J. So I can divide by determinant of J and then multiply by the conjugate of J. And that gives me the inverse of the Jacobian. Now I can construct the inverse kinematics problem to find out what are the thetas needed in terms of x dots. So I have theta dot here equals to J inverse times V dot, Cartesian velocities. And as you can see here, the reference frame is 3 and 3. So J inverse has to be in reference to frame 3, and V has to be in reference to frame 3. Or J has to be in reference to frame 0, and V has to be in reference of frame 0. So in this case, if I open theta up, so I have theta 1 dot and theta 2 dot, and then I put here the inverse of the Jacobian, and I open the velocities up to x dot and y dot of frame 3 relative to frame 3. Now all I need to find is find theta 1 dot and theta 2 dot, what their values are out of these two quantities. So if I multiply these, I'm going to have theta dot 1 equals to x dot divided by L1 S2. And I'm going to find theta 2 dot to be equals to this quantity in terms of x dot and y dot. Now I want you to notice that both of these also look like they have S2, and they have S2 here and C2. And the reason for this, remember, thetas are part of the Jacobian, always. So at every moment in time, these thetas change, which means that the Jacobian changed. And that means also theta dots change as well. Let's take another example here that shows momentary singularities. And this time we're going to look at interior singularities. So we look at the Puma 560 robotic arm. This manipulator has 6 degrees of freedom, 6 revolute joints. And we're going to have to find here one or more momentary interior singularities for this arm. So I'm going to start here with one case, which is at the wrist. It's called wrist lock. So what you see here is the wrist, and the wrist in the Puma 560 has 3 revolute joints. So you have joint 4 and joint 5, and this is joint 6. And all of the 3 coordinate frames of these 3 joints meet at the same point. Okay, so this particular singularity happens when joint 5 is rotated such that joints 4 and 6 are lined up. So the action of joint 4 that rotates about this axis and the action of joint 6 that rotates about this axis, okay, both of them are lined up, which means that if you would like to move the end effector about this axis, whether you move joints 4 or joint 6, it gives you the exact same motion. So that makes you lose a degree of freedom, and that makes your robot momentarily singular. Now, if you get out of this configuration, of course, for example, Z4 becomes upwards, Z6 becomes upwards, that means you have your degree of freedom back. Another case when you have interior singularity is the elbow lock. What we're looking at here, we're looking at the top view of the Puma arm. This is the base right here, and this is the lower arm, and this is the upper arm. So this case happens when joint 3 is situated such that the upper arm and the lower arm, both of them are lined up. So when they're both lined up, that means the elbow is locked right here. And if you look at the wrist point right here, and the origin of frame B, which is the z-axis of the ground frame, there's a line here, that's the degenerate direction, which means that the arm can no longer move along this line. So this wrist point can no longer move along this line. If you want to push it forward, of course the elbow here is locked, it cannot go any further. If you want to push it backwards, again the elbow is locked, you cannot push it backwards. Again, this happens momentarily because of the configuration. If you move joint 3 out of this configuration, of course, the degree of freedom comes back, and then you have that momentary degree of freedom loss gone. The third case is the overhead lock. So we're looking here again at the Puma arm side view. And this case happens when the wrist is lined up with the axis of motion of joint 1 or joint 0, the ground frame. So this is the Z of the ground frame and joint 1. And when the wrist here is lined up with this Z0, the wrist can no longer come out of the plane. So in this case, the plane that contains the upper and lower arms, this plane here, is something that the arm cannot come out of until you change the configuration of the arm. Once you change the configuration of the arm, you get out that momentary singularity, and then the arm will be again fully operational.